Okay, so let us begin with, as usual, a recap. The last thing we were doing, we were talking about decoding Reed-Solomon codes. Okay, so let me quickly remind you what the entire idea was. Okay, so you have a, so the first thing is we are going to view everything as polynomials, if you remember correctly from last time. So we are going to say you have a code word polynomial which gets transmitted through the channel, and that is modeled as addition with an error polynomial to get a received polynomial. Okay, so this is what you are given, and each of these polynomials has n minus 1 terms, right. So those are all understood. So r of x becomes c of x plus e of x, and the goal is to find e of x, okay, right. The goal, that is the idea of this decoder. You have to find c of x, of course, from r of x, but we try to find e of x. Okay. So for that purpose we do basically bounded distance assumption, and we say that there are, let us say for instance, w errors in e of x, only w non-zero terms out of the possible n terms, okay, only w of them are non-zero, and we use a notation for it. Basically we say it is y1 x power I1 plus y2 x power I2, so on till yw x power IW. Okay. So we assume that the error polynomial is in this form. Okay. So that is the first simplification, the bounded distance decoder assumption. Okay. So when I say BDD, it is bounded distance decoding. Okay. So you make that assumption, and if your RS code is, let us say, T error correcting, we usually assume that this W is less than or equal to T. Okay. So you have at most T errors. Okay. So the first task is to find syndromes. Okay. The syndrome, the ith syndrome is defined as R evaluated at alpha power I. What is alpha? Alpha is the well, it belongs to some Galois field, okay, used in constructing the code. Okay. So okay, so hopefully it is clear what I mean by alpha. Okay. So R of alpha, and we saw that this is the same as E of alpha power I for I between 1 and 2t, right. So the first 2t powers of alpha show up as rows in the parity check matrix. So alpha power I will, C of alpha power I will be 0. So if you evaluate R of alpha power I, you get E of alpha power I. Okay. So in effect you can write Si as summation. Okay. So I will just write this notation in shorthand, since I am repeating everything. So hopefully it is clear to you what I mean. Yj xj power what I. Okay. And what is this xj? Xj is alpha power I sub j. Okay, where this guy is the error locator. Okay. So these SIs can be evaluated, and you have nonlinear equations. Okay. So these are basically power sum equations, okay, sums of powers of x. Okay, you want to determine the error locator. All right. So the goal is to find obviously the error locator xj and the error magnitude yj. Okay, you have to find both. Okay. So the trick, the main trick is to Once again think of polynomials and define a syndrome polynomial which is Si x power I, and then also define an error locator polynomial which is product 1 plus j equals 1 to w. Okay, so, these are the two polynomials we define. Okay, we define a syndrome polynomial and an error locator polynomial, and we in fact think of this polynomial in its expanded form. It will be 1 plus lambda 1 x plus so on till lambda w x power w. Okay. And then it turns out you can show in the product s of x times lambda of x coefficients of x power w plus 1 through x power 2 t equals 0. Okay. So, this gives you linear equations for the lambda. Okay. So, from here you get linear equations for lambda j. Okay. So, basically the way you, then you have to worry about when that linear equation is solvable, etc., etc. So, for that we use this definition of a matrix which I define as m of mu for some mu between 1 and t. What is m of mu? S mu minus 1 all the way to S 1, then S mu plus 1, S mu, S 2 all the way down to S 2 mu minus 1 all the way to S mu. Okay, this is the matrix. Okay. So, you start with mu equals t, okay, and find the determinant of this matrix. If this matrix has non-zero determinant, then you conclude that w equals t. If it has 0 determinant, then what do? Try mu equals t minus 1. Okay. So, that way you keep reducing it till the determinant becomes non-zero, at which point you would have found w. Once you found w, you can simply invert this matrix, then multiply with what? M of w inverse multiplied with S w plus 1, okay, S w plus 2 all the way till S 2 w. Am I right? This will give you lambda 1, lambda 2, lambda w. Is that okay? So, you are not done at this point, right? You have only found the error locator polynomial. From the error locator polynomial, you have to find the error locators. So, basically you go through your Galois field and find all the roots of lambda of x. Okay. If you get exactly w distinct roots, then you have succeeded in your decoding. If anything else happens, something has gone wrong. Okay. So, you find the x. Once you find the error locators, how do you find the magnitude? Go back and plug in into the syndrome expressions, you get linear equations for the error magnitude, solve them once again, get your answer. Okay. So, that is the idea behind the decoding. So, it is quite a lengthy process, and it will hardly ever show up in an exam. Okay. So, maybe you should not pay attention, but it is good to know that this is the method. Okay. And one thing I should warn you is, in practice there are lots of Reed-Solomon decoders around. Reed-Solomon codes are the most common codes out there. Okay. So, hard disks have them, your CD drives have them, DVD drives, I mean everything has Reed-Solomon codes in them, and nobody will use this decoder. Okay, so of course, there are other versions of this decoder which are a little bit more sophisticated, much more simpler to implement, etc., etc. Okay, so those are the versions that they will use, but the basic trick will always remain the same. You will define a error locator polynomial and use the fact that syndrome times error locator will give you some linear equations. Okay, ultimately that is what you use. Okay, and ways of solving those things smartly. There are in fact, for instance, an iterative way of finding lambda of x, things like that is what is used usually. Okay. All right. So to complete the picture and just to show you how it really works, we are going to do a very simple example. Okay, so it will be a contrived example that I will come up with to give you a feel for how it works, and then we will just move on. Okay, so I will take a very toy example. Of course, in reality, in practice, you would use much larger fields, but if I use large fields now, then we can't do the computation that easily. Okay, so we will use a very small field and we will try and correct 2 errors. Okay, just to make the problem a little bit more interesting. Okay, all right. So that is the example. We are going to stick with an alpha, let us say in GF 2 power 3. Okay, so alpha power 7 is 1, and then alpha power 3 is 1 plus alpha. So, it is good to make the table. Okay, so you have 0 1 alpha, alpha square, alpha power 3 is 1 plus alpha, alpha power 4 is alpha plus alpha square, alpha power 5 is what? Alpha squared plus alpha plus 1, alpha power 6 is, what is the only other missing? 1 plus alpha squared. Okay. So, you can keep this table with us to help us in the computation, and let us say n equals 7 and t equals 2. Okay. N is 7 and t is 2, what are the 4 roots? The 4 roots of my code, or 4 zeros of my code, sorry, are alpha, alpha square, alpha power 3 and alpha power 4. Okay. So, those are the 4 zeros of my code. Okay. So, if I have any code word of any received word, I will compute syndrome by plugging in alpha, alpha square, alpha power 3 and alpha power 4. Okay. So, of course, for the example we need to come up with a received code word first. Okay. For that we need a, what do you need to come up with the received code word? You need a transmitted code word. Okay. So, for that you have to compute the generator polynomial and play around with it. Okay. So, let us do that first. The generator is going to be x plus alpha times x plus alpha squared times x plus alpha power 3 times x plus alpha power 4. Okay. So, the first person to compute this will get 5 bonus marks in the next quiz. Let me see who is going to do that. Okay. So, the easiest term is the x power 4th term, and the next easiest term is the constant term. Okay. What is the next easiest term? X power 3 is also not too bad, right? X power 3 you have to simply add alpha, alpha square, alpha power 3. So, you get alpha power 5 x power 3. Is that okay? Did I make a mistake? Oh, alpha power 3, okay. Okay. What about x squared? square is simply x square, then x alpha. Okay. So, so this is g of x. So, let us say we transmit the code word c of x, which equals the same thing. Okay. So, and just to be consistent with the way we have been writing, so I will write c of x like this. Okay. And to make our computation of syndrome easy, what is a good R of x to assume? Okay, remember, you want to make your computation of syndrome easy. So, what should you get rid of? So, the last two terms you can get rid of, right. So, it is maybe a good idea to assume that the R of x is alpha power 3 plus alpha x plus x squared. Okay. People are staring at it like I am doing some crazy stuff. So, I am just saying E of x is something. Okay. I know the E of x already, no point in doing the decoding to find out, but let us say as you assume you did not know what C of x was. Okay. So, this is your R of x. Okay. So, this part is unknown to you. Okay. Let us suppose, just for the sake of showing how the decoder works, right. Of course, in real life you will have a much larger field and you cannot find out just by looking at the received polynomial what the code word would have been. Okay. So, it is not possible, but just to make our job easier we will do that. Okay. So, there are two errors, okay, and I have clearly I know where I have introduced them. So, I have to now go through my decoder and make sure that everything works out fine. Okay. So, you have to compute the 4 syndromes, right. What are the 4 syndromes? S1, is alpha power 3, S2 is alpha power 4, S3 S3 is 0 and S4 is alpha power 5. Okay, so these are my quick answers, please do check if it is fine. It's fine. I have one confirmation, one more confirmation. Okay, good. So, these are the 4 syndromes. Okay. So, the next step is what? You have to make that matrix and find out if it is singular or not. I know for t equals 2 it is going to be singular already, but anyway let us pretend that we do not know it. We start with m of t, which is m of 2, right. That would be, what do I put here? S2, S1, oh S1 is alpha power 3, I am sorry, and then S3, S2. Is that okay? So, clearly determinant is non-zero. Is that okay? All right. So, we guess that determinant is non-zero. Determinant is what? It is actually alpha, which is not 0. So, W equals 2. Okay. So, we said two errors have occurred, and then we go through and find lambda 1, lambda 2 as inverse of m of 2. What is inverse of m of 2? What is this entry? No, you will also have to divide by alpha, right. So, the overall determinant is alpha. So, alpha power 3 alpha power 2. Okay.
Why?
Let me write the original matrix here, looks like okay. So, this was alpha power 4 and alpha power 3, alpha power 4, this was my matrix. Alpha square 0 and really there should be something else. 1 by alpha we have already done, but 0 and alpha square have to be is okay.
Has to be
Okay, you are happy? Is this? It's easy to check that it is the inverse. You just multiply the two matrices and see if you get I. You can check that you will get I. So, this is a valid inverse. Okay. So, then they have to multiply this with S3 and S4. S3 is 0, S4 is alpha power 5. S4 is, it is not alpha power 5. Yes. Two other people confirmed it to me. One plus alpha power 5 is alpha power 4. Is that what you are saying? How many of you say S4 is alpha power 5? Nobody has actually checked, is it? After we do the whole thing, you are telling me the final.
I am getting alpha power 6.
Alpha power 4. Alpha power 4. I think I remember the two people who shook their heads.
Alpha power 10 is alpha cube.
Alpha power 8.
4.
Alpha.
Okay, 4, huh? Okay, all right. We go back and change this. So, what will change if I change this? Nothing here will change, no. So, S4 does not play a role in this, only in the next part. So, instead of 5, I will have 4 here. Am I right? So, this is simply alpha power 6 and 1. Okay. So, my lambda of x basically becomes 1 plus alpha power 6x plus x squared. Is that okay? Are you wondering how I quickly multiply the two matrices? It's just an easy multiplication. It's just 0 alpha power 4, right? Simply scale the second column by alpha power 4. You get alpha power 6 and 1. Okay. So, your lambda of x becomes 1 plus alpha power 6x plus x squared. Is it okay? Yes or no? X squared is the correct coefficient. Okay, that much I am sure about, because we introduced errors in locations 3 and 4. So, alpha power 3 and alpha power 4 are the error locations. So, the inverses are also the same, and multiply together you should get 1. Okay. So, this you have to find roots. Okay. So, what are the roots? You can check that the roots will be alpha power 3 and alpha power 4. Okay. So, if you want, you can check this, they have to be the roots according to our computation. No, roots are this. Then the error locations will be inverses of this, which will also be the same. That is the trick. Okay. So, alpha power 3 and alpha power 4. Okay. So, the error locations are x1 equals, if you want, alpha power 4, and x2 equals alpha power 3. Okay. All right. Is that okay? So, you have an error in the third location and the fourth location. So, you know E of x was of the form y1 x power 3 no y2 x power 3 plus y1 x power 4. Okay. So, you can play around with this 1 and 2, it does not really matter, I mean it is just the way I am trying to be consistent here. So, S1 which was alpha power 4 was actually equal to, instead of x I should put alpha here, alpha power 3 y2 plus y1 alpha power 4, okay, and S2 which was again alpha power 4 is equal to alpha power 6 y2 plus alpha power 3, is it okay? Sorry about that. Is it okay? S2 and y1 alpha. Okay. So, you solve these two, you are going to get y1 equals 1 and y2 equals alpha power 5, alpha power 3. Okay, you can check that. Okay, so it works out. So it works out quite consistently. It's not a problem. I mean, we will get the right answer. Okay. So if you want, you can go back home and take this example and play around with it a little bit more. You know, if you do not believe any of the stuff that we did, you can add one error, for instance, and check that m of 2 in fact works out to 0 determinant. Okay, so that you can check, and then you will see m of 1 is okay, m of 1 is very easy to correct, you will correct it. Okay. So this is how a Reed-Solomon decoder will function. Any questions, comments, insights? Seems simple. Okay. Okay. So this is in a way a significant stopping point in the course, as in the we have come to a stage in the history of coding, so to speak, where you have achieved something quite significant. Okay. So Reed-Solomon codes were considered the crown jewel of algebraic codes for a long time, and they are still used. Like I said, it is the most popular code around. Okay. Any device you take is very likely to have a Reed-Solomon code or a BCH code for that matter. Okay. And we see that encoding is very easy, you have a shift register circuit. Decoding is also equally easy. Okay. You only do computations with a small lookup table, which is very trivially implementable today. Okay. So today Reed-Solomon codes, I mean I can list the number of places where they are, I mean everywhere. Okay. Any place you imagine, you have Reed-Solomon codes. Okay. So they are very popular, and they deserve their place also. Okay. So what we are going to see beginning from this lecture onwards, beginning at this moment onwards, is something very different from what we have been seeing so far. Okay. So far we were looking at algebraic codes. Okay. Basically what were the main characteristics, so to speak, of algebraic codes? You used finite fields for the construction, right? You get a you get a certain design distance, right, and you have good bounded distance decoders. Encoders are simple, but usually encoding is not so complicated, as you can imagine. In the worst case, it is simply a multiplication by one big generator matrix, and you can do it, it is not a big problem. So let us not worry about the encoder. They have good, well not good, very efficient bounded distance decoders. Okay. So for a long time the view of coding was that it's not save changes, what is this? Okay. So, the way people viewed codes for a long time was that you have a certain communication channel, okay, on which you have done a lot of work, so that you have bits going in and bits coming out. Okay. So, for a long time people were trying to do codes, an encoder and a decoder will sit outside here. Okay. So, this was considered as the place for the encoding and decoding. Okay. So, coding was seen as primarily a mechanism for correcting errors. Okay. So, that is why they are called error correction codes, and this was how codes were used for a long time. Okay. So, you have a channel into which you are putting in some bits, you are getting bits out. Okay. What happens inside the channel, or how is the channel physically realized, what kind of electronics you do on the channel or signal processing you do on the channel is completely hidden from you. Okay. Some bits are going in, bits are coming out. There is some probability that the bits might be in error. Okay. So, you either had a binary symmetric channel kind of model, or in fact better model or a more simpler model was the bounded distance model. You always knew that with very high probability you would have a maximum of, let us say, some 8 errors, 8 byte errors or 8 bit errors or whatever. You had a bound on that number. Okay. Once you had that, what did you do for designing? You used an algebraic code. Okay. It made a lot of sense to use an algebraic code because it has a design distance, you know, it is MDS. So, for the given distance it is probably a very efficient code, and then you have good bounded distance decoders that can be implemented. Okay. Everything was fine. Okay. So, as electronics advanced, okay, people slowly started thinking of coding as part of the signal processing in the communication process itself. Okay. Instead of thinking of coding as coming in a separate outer box, can we move coding inside, okay, closer to the modulation. Okay. So, let us differentiate between coding and modulation. So, for coding you are thinking of bits, message bits are getting converted into code words. What is modulation? In a very loose way, and you might have defined it very rigorously in communications, I do not know digital communications, but the way to think of modulation is bits are getting converted into signals, right. So, electrical signals. Okay. Is there anything to gain from pushing coding from the outside closer towards modulation and thinking of the whole thing as one big operation? Okay. So, people started in the late 70s, early 80s, or even maybe early 70s talking about what is called coded modulation. Okay. So, this is a classic error correction picture. It was called forward error correction for a long time, error correction or FEC. Okay. And then people started talking about coded modulation. Okay. So, here you think of codes as part of the signal processing needed for communication. Okay. So, instead of thinking of it as some box that sits outside of my entire digital communication device and fixes errors that I occasionally make, can I move it inside the modulation part of my design, so that to give a better performance. Of course, there has to be a benefit, okay, right. If there is no benefit by doing coded modulation, nobody would do it. Why bother? You just wait with the same pictures before encoder decoder and proceed. First of all, you have to be sure that there is some benefit in doing coded modulation. If you do that, do you gain something? Okay. So, does your design become better? All those things are questions you have to ask. Okay. And of course, the answer was yes. Okay. So, that is why people did that. And the next thing you have to worry about, at least in those days, the VLSI part of things were not so advanced. Okay. So, you still had to deal with almost hand optimization of circuits kind of thing. Okay. So, if you are doing those kind of things, then doing coding at the signal processing level is probably more difficult. Okay, so you will have to deal with, I mean maybe I will explain in more detail why it is a little bit more difficult, because it requires a lot of memory, right. Your block length is going to be 2000. Okay. Previously you were simply dealing with 1 bit at a time independently inside in the signal processing part. Okay. Now if your block length is 2000, you can't simply deal with it 1 bit at a time if you are doing coding inside, right. You have to wait for all the 2000 signals to come in, which means you have to process a huge block of data and you have to do signal processing for it, which might be difficult. Okay. So that was a significant roadblock for some time. Okay. Once that problem was solved, once VLSI became advanced enough, then it made obvious sense to do coded modulation. Okay. So what I am going to describe next is a very simple picture of modulation in a way that will be useful for us, okay, way that will be useful for coding. It is fairly rigorous. If you do your digital communication course, you will see that that is how most modulation schemes are. Okay. But if you see it first time, you might think I am making some mistake or I am making a huge approximation. It is not a big approximation. Okay. So how do we think of modulation? So we will use this 2-dimensional vector kind of representation for modulation, which is quite, in fact we will only use 1 dimension, but just for the sake of it I will draw pictures. Okay. So you can think, so like I said, modulation is the process by which bits are converted to signals suitable for transmission. Okay. So I am not going to redo digital communications here, but the way we will model this is, instead of thinking of signals, we will use the vector space representation for signals, okay, which will give us a simple alphabet for the signals, okay, and we will only deal with the alphabet. Okay. And we know that you have, you can think of the signals, you can make a orthogonal basis, orthonormal basis for them, and then express your signals in terms of those bases. So you will get a point in the constellation, so to speak, for the signal. Okay. So instead of thinking of the whole signal, we will simply think of a point in a constellation, and in fact we will mostly use only a 1-dimensional constellation. Okay. So we will assume these signals come from a 1-dimensional constellation. Pretty much for the entire course we will only deal with the 1-dimensional constellation. In fact we will mostly, so this is in the vector space notation. Vector notation or representation, we will only look at 1-dimensional constellations. In fact we will not even look at generic 1-dimensional constellations, we will simply look at what is known as BPSK. Okay, what is BPSK? It is just 1 dimension, okay, and you have just 2 points in the constellation, which I will normalize to +1 and -1, and I will say 0 maps to +1 and 1 maps to -1. Okay. So this is how you represent a constellation, right. It is 1 dimension, you have simply a line and 2 points in that line. This is binary PSK, it is a very standard constellation that people use. Okay. So we will not go into any detail on the digital communication part of it, we will simply directly use this BPSK constellation for almost the entire course. Maybe later on if it is needed, I will mention how to do other constellations. Okay. It is not too difficult once you understand how BPSK constellation works. Okay. So what does our encoder now look like? Okay, encoded modulation. Okay. So in fact we won't even look at really complicated ways of doing coded modulation. There are ways of integrating the coding with the constellation, etc., etc. We won't look at all of that. We will simply use a coded modulation, which is a very simple form of things. Basically what we will do is we will take k bits with the message, which we will call M, go through a code. Okay. So this is the code part of it, encoder, let us say it is an NK binary linear code. Okay. Okay. All right. Even if your code is a Reed-Solomon code, right, you can always ultimately come back to some binary linear code, right. So you are going to represent all your alphas as some number of bits only finally. So this is a good picture to cover that case also. Okay. So you get n bits which make a code word which I call C, and then I will have a BPSK block which represents. So, this will output n symbols. I will get a symbol vector which I will call S. Okay. What does the BPSK block do? If my bit is 0, it is going to make it plus 1. If my bit is 1, it is going to make it minus 1. Okay. Is that okay? So, I have n symbols. Okay. There is a wonderful abuse of notation you can do, okay, to write this S in terms of C. Okay. So, it is very common in MATLAB, it will work very well. Okay. So, write it as 1 minus 2C. Okay. So, of course, it does not make any sense in binary field, right, 2 is 0 and then you will not get anything. Okay. So, you have to imagine now that this 1 and zeros are actually integers, and then you do 1 minus 2C, you get minus 1 and plus 1. Okay. So, it is just a simple shorthand notation to represent BPSK. It is not crucial, but it is just good, it simplifies some notation later on. Okay. All right. So, now I am going to rely on your knowledge of digital communication to say what will happen if the signal goes through a additive wide Gaussian noise channel. Okay. So, there is a very common model which is called the AWGN model, additive wide Gaussian noise model, under which in the vector space notation something very simple happens to the signal. Okay. What happens to the signal? A random variable gets added to each symbol, either plus 1 or minus 1, and that random variable is independent from symbol to symbol, and it has some variance which we will call as sigma square, okay, which might be some n naught by 2 in your white noise assumption. Okay. So, we will simply say sigma square. Okay. So, that will be my noise vector. Okay. So, I will call it Z. Okay. This I will say is distributed normal with mean 0, variance sigma square IID. Okay. So, this is the assumption on the noise. Okay. So, there is a very rigorous justification for it. You can start from a set of signals, let us say 2 signals, express it in terms of a basis like this, and then send that signal out and assume some n of t gets added to it, and then you design an optimal front end which is called the match filter. You design that, and then you look at a sufficient statistic which will be just this, okay, which will be some noise vector being added to the representation of the signal in the vector space notation. Okay. So, this is a very complete and accurate representation of what happens to a full fledged electrical signal in practice. Okay. So, this is good enough. Okay. So, you get a received vector R, okay, from this. All right. So, R now remember is a real vector. Okay. It belongs to the n dimensional real space. Okay. So, it is a real number. It can take any value, right. The way I model Z is simply a normal variable, normally distributed variable, 0 mean and variance sigma square. So, it can take any value from minus infinity to infinity. Okay. Of course, the larger values are more and more unlikely, but still it might take those values. So, R can theoretically be distributed over the entire real line. Okay. So, now comes the crucial steps. So far you might say I have not done anything very different. I mean, I am not, what is coded modulation here? The crucial idea here is that the decoder will work directly with R. Okay. So, that is the big difference. Okay. The decoder will directly work with R and produce an estimate of C hat. Okay. So, maybe I should rewrite that a little bit more clearly. Okay. No, decoder. So, that is why that is the way I have combined the coded and coding and modulation. Okay. So, I am going to run a decoder directly on the received values without doing any bit by bit, symbol by symbol demodulation. I will not do any such thing. Okay. But of course, that is one choice. I will talk more about that later. Is that okay? So, this is a big difference. Okay. So, hopefully you agree with me that this is very different from the decoders that we have been seeing so far, right. These decoders we have been seeing so far work in some Galois field, right, for the Reed-Solomon code. If you are using a Reed-Solomon code here, they work in a Galois field, not in the real field. Okay. They makes no sense to use them on the real field, right. There is no direct way, you can't compute a syndrome, right, it would not make any sense, there is no roots, no polynomials, nothing. Okay. It becomes a problem in what is known as detection or inference or learning or whatever you want to call it. There are so many different areas these days. Okay. So, all of them are pretty much the same, we can call it decoding, which is okay, it is not too bad. Okay. So, it is important to understand what is going on here in more detail, we will see it in more detail, but this is the picture in general that we will be looking at for pretty much the rest of the course. Okay. So, we will look at different coders, encoders and decoders which work in this picture. Okay. And like I said, there is a way in which you can study what is called capacity of these systems and show that a system like this, if it works well, will be about 3 dB better than a system like what we had before. That is a rough number. Okay. So, maybe it will be more. So, basically there is lots of signal power that you can gain by doing coded modulation directly as opposed to only dealing with bits, that is the idea. Okay. So, roughly we may not have time to see that also, maybe we will see it, we will see, okay, depending on how much time we have. Any questions about this picture?
Still we don't have a temp vector, so again we have to anyway C cap is the estimate of the
Code word.
code word.
Yes.
So again we have to anyway use
No.
to get back.
No.
This is not R vector.
It is not R, the R vector that you are thinking of. See, C cap is supposed to be a code word. So, if you are doing systematic encoding for instance.
So that is guaranteed to be a code word.
Yes. No, well, let me not say estimate of code, but you have to think of it that way. From that you are going to compute the message as, let us say, systematic, let us assume systematic encoding. So, if the first k bits of C cap you will say is M cap, that is all, you will not do any further decoding after that, it is supposed to be directly that. Okay. So, I am going to ask more questions. So, if you have any questions, it is a good time to ask, because typically people misunderstand something when I write like this. It seems very clear when I write it, but when I ask the next few questions it seems a little bit more confusing. Usually people get confused by that. So, stare at it for a while, hopefully you understand these things. Is it okay? Okay. So, one thing I have to clarify is the notation. Okay. I will happily kind of, I do not want to say waltz, but let us say move here and there between random variables and values taken by them. Okay. So, I will not distinguish between those two too much in my notation. Okay. So, for instance, here the z vector I have said is a random vector which is normally distributed. In fact, even the C or the S is a random vector, right, message is supposed to be random. So, everything is random, but we are not dealing with them in that fashion, right. So, we are thinking of them as the values taken also, you just think of that also as the same thing. Okay. But remember, these things have distributions, so that is how they look. Okay. So, the first question I am going to ask you is the following, it is a very simple question. Let us suppose we look at one particular symbol. Okay. So, let us say Si, okay, one particular symbol, it is going through the channel. So, one Zi which is normally distributed with 0 mean and variance sigma square goes in. What will be the distribution of Si if you assume equally likely messages, etc., etc.? It is going to be uniform, it will be discrete distribution. So, it will take only two possible values, -1 and +1 with probability half. Okay. So, this is so let us have some notation for it. So, we will say uniform with curvilinear, this curved brackets -1 and 1. Okay. So, it is curved brackets. So, I get an R sub I. Okay. All right. My first question is, what is the distribution of R sub I? Everybody does this. That is what I like most about. What is Gaussian? It's this. Okay. So Ri is going to be, you are right, I mean you are essentially right. So, it is going to be two Gaussians added up. So, you can think of it as half normal -1 sigma squared plus half normal plus 1 sigma square, right. So, this is a very, I mean I am writing a bad notation here. So, hopefully you see what it is. If you draw the PDF of Ri, how will it look? Okay, this is the PDF, it will look like this, okay, depending on the value of sigma, which if we will assume is small enough compared to minus 1 and plus 1, it will look like this. Okay, trivia question, what is this height?
Neglect the other. 1 by 2
no
root
e
2
power
pi.
minus 1 by sigma square, all that won't come. E power minus 1 by sigma square.
No, why will that? So the other one can be neglected.
There will be no e power minus 1 by sigma square. Is everybody agreed on that? In that height? Okay, good. What will that height be?
1 by 2 root 2
It will be something. There will be a small factor, right? E power minus 2 by
sigma square.
sigma square will be there. Why are you saying there will be no e power minus 2 by sigma square?
So you assume sigma to be much less than 1.
You can't take it will be a small term, but if it will be there, right, there will also be a 1 by root 2 pi sigma square before that. Okay, so you know what about this height?
M.
The same.
E power minus 1 by 2 sigma square and 1 by root 2 pi sigma square.
Anyway, so hopefully you know enough about normal distributions to compute these 2 points. Okay, you have to write the expression. Okay, so f of Ri will basically be this expression, half 1 by root 2 pi sigma e power minus Ri plus 1 by Ri plus 1 squared by 2 sigma squared plus 1 by root 2 pi sigma e power minus Ri minus 1 by 2 sigma squared. Okay, so, this will be the actual full expression for f of Ri. Okay. The question I asked about that height was basically plugging in Ri equals plus 1 or minus 1. Okay, so, this will be an even function or not, it will be an even function. So, you can either put plus 1 or minus 1, you will get the answer. Okay. And the question about this height was putting Ri equals 0. Okay, so, you get some other answer. Is that okay? So, that is the PDF. Okay. So, if you are looking at, if you are sitting at the receiver and looking at Ri will take values around plus 1 and values around minus 1, am I right? Okay. So, this is how the picture will look for BPSK AWG. Okay. So, there is no, I am not talking about coding here. Now, suppose I ask the question, what is the best estimate of SI given Ri? Okay. So, given Ri, suppose I want to find SI cap, okay, nothing, I ignore everything else. Okay. So, it is very easy to do that, right, you can do an ML estimate, any Ri greater than 0, then you decide SI cap is plus 1, if Ri is less than 0, you decide SI cap is minus 1, that is the best thing you can do for a particular I. Is that okay? That is important, you ignore everything else, for the particular I, that is the best you can do. Okay. So, let us write that down also, ML estimate or the maximum likelihood estimate. Okay. You can also compute it correctly. I think most of you should have enough experience to know what I mean when I say this. Okay. SI cap is plus 1 if Ri is greater than 0 and minus 1 otherwise. Okay. So, basically you can do what is called slicing. Okay. So, you can slice Ri, this is a very crude term to use to express this basically. You do a slicer, it will work like that. Okay. So, let me write that down also. If you have SI and Zi normal 0 sigma square is getting added to it, you get a Ri you slice. Okay, the picture for a slicer is this. Okay, so normally the things are not marked, so basically it is +1 and -1. So this is the slicer. You would get a SI cap. Okay, so you can think of it as the best possible estimate you can have for SI given that particular Ri only. Okay, so you are not given anything else, only given Ri. This is the best possible estimate for SI that you can do. Okay. So the slicer is also called a hard decision. Okay, hard decision device or hard decider. Okay, so it say slicer makes hard decisions. Okay, so this is called a hard decision, and this Ri is called soft. Okay, so the reason why you would say Ri is soft and SI hat is hard is when you can see why that makes sense. So suppose I am given a value of Ri. Suppose in this scale this is +1. Suppose I am given a value of Ri which is, let us say, something like 0.8. Okay, Ri is 0.8. Okay, when I say Ri is 0.8. Okay, so it is close to +1, or another possible value for Ri could be, let us say, 0.1. Okay. Okay. So if I say Ri is 0.1 and at one time, and I say Ri is 0.8, the two mean something different. Okay. On the other hand, if I slice and look at what came out of the slicer, for both I would get the same +1. Okay. So the slicer loses information in some way. Okay. Right, it loses that softness of information. Okay, so it loses the belief, or so to speak, of how confident you are that SI cap is +1. Okay, so that's something that it loses. But remember, given Ri alone, the slicer is the best you can do. There is nothing else you can do. Okay, it's the best you can do. But having Ri itself might be more useful because it has more information in it. Okay, value can mean something. Okay. So one choice for your decoders, remember there was a decoder I drew working on R. Okay. One choice for your decoder is a hard decision decoder. Okay. So let us say I do a hard decision decoder. So what is a hard decision decoder? Okay. So when you get R from before, okay, so this R is coming from before it. So in the hard decision decoder, the first thing you would do is slice symbol by symbol. Oops. Okay. So you would get something, let me call that y, the vector y. Okay, what is this vector y? Basically this is what you get after slicing Ri. Okay, so y is y1, y2, yn, yi is -1 + 1, and yi is the sliced version of Ri. Okay, so yi is okay. Then what you can do is you can go from y to some other, okay, maybe y was not a good choice because I have used z for something else, but let us say from y you go to w. Okay, how do you do that? You do inverse BPSK. Okay, you can write an expression if you like for inverse BPSK, which will be 1 minus y by 2. Okay, so that is the inverse BPSK. Let us say you get a w. Okay, now remember w now is n bits. So at this point you can run your syndrome decoder. Okay. So, this is a hard decision decoder which will produce definitely a estimated code word at the output. Okay. So, remember when I do slicing symbol by symbol, given Ri alone, Yi, that is the best possible thing I can get for Yi. There does not seem to be anything suboptimal given that symbol, but overall there is some suboptimality here. Okay. So, I will come back and comment on this later on. Okay. Once I have come to this hard decision versions, I can do a inverse BPSK, and then syndrome decoder is optimal, right, it is an ML decoder. So, you do an ML decoding, you get the CCAP. Okay. In fact, from the code word C to W, you can draw a binary symmetric channel. Okay. So, you can do that, it is equivalently a binary symmetric channel. Remember, how did I get R? R came from ultimately some code word C, right. You can do an equivalent channel from C to W, and that will be a binary symmetric channel. What will be the transition probability of the binary symmetric channel?
Greater than 1.
Yeah, probability that the noise is strong enough so that your slicer makes a error. So, what will be that probability? Q of
1.
Q of 1 by sigma. So, Q of 1 by sigma. Okay, so you remember, hopefully you remember enough of digital communications to know this. So, it is the probability that the slicer makes an error, it is Q of 1 by sigma. So, from the code word to W, I have a binary symmetric channel. So, clearly the syndrome decoder is an optimal ML decoder, you get it. Okay, so, this is the hard decision decoder, and this is the same picture like we had before. You are really not doing coded modulation here. Okay. It sounds like I am doing coded modulation, but the slicing symbol by symbol is basically a independent demodulation. I am not taking the coding into account when I do slicing symbol by symbol. Okay. There is some information loss here. Okay. The reason is R, the bits, the elements of R are not independent. Okay. R1, R2, R3, if you look at all of them together, they are not independent. Clearly, they are not independent, right. The code words form only a smaller subset of the all possible 2 power n vectors. Clearly, the vectors of the elements of R are not independent. So, you can't treat them independently and slice happily symbol by symbol. You have to view it as one big block and decode to the possible code word. That is the optimal thing to do. On the other hand, if you decide my complexity is too high, I can't do all of that, one choice is the hard decision decoder. Then you are back in the same old picture as before. Okay, the syndrome decoding world, where you simply do come back to bits and you are happy. Okay. So, what we will see next is what to do if you do not want to do hard decision decoding. Okay. So, anything that is not hard decision decoding is called soft decision decoding. Okay. So, see, all of you know enough of coding already, I do not have to do anything. Okay. Okay. So, this I should remind you is kind of a modern idea, it's been around for all the time, all over the place, but in an implementation sense it is definitely a modern idea. Okay. So, I will comment later what I mean by this later on. Okay. So, as we go along you will see what I mean. But soft decision decoders have been around since ages, they have been around since 70s, definitely what is known as the Viterbi decoder is clearly a soft decision decoder. They have been around for a long time, but they have been kind of resurrected recently and so much studied in so much more detail, and several suboptimal soft decision decoders are out there today which work really well in practice. Okay, so, as an engineering solution, soft decision decoding is pretty much taken over today. Okay, so, many of the new devices, new implementations you would have will be soft decision decoders. Okay. On the other hand, I should also comment that soft decoding of algebraic codes is really hard. It's interesting. Okay. It's not so easy to do soft decoding of algebraic codes. There are algorithms, okay, there are definitely very good algorithms that give you good soft decoders, but it is still kind of non-trivial to come up with a very nice algorithm which works well in practice. So, remember in practice we are going to look at fields which are as large as 2048, okay, and rates that are large usually, okay, rate 0.9. In those cases most of the soft decision decoders known available out there for algebraic codes do not work that well. Okay. So, one of the greatest open problems in coding which still to my best of my knowledge remains fairly open is coming up with good soft decision decoders for large algebraic codes of high rate, okay, large field algebraic codes with high rate. That is kind of an open problem. I see people are writing down the problem, but it is unlikely that it will be solved in the future, or maybe people actually, I should say, today in coding people are not interested in that problem. The reason is there are other codes which are not so, in a way, so to speak, algebraically structured as Reed-Solomon codes and all that, but they have good soft decision decoders and they have taken over pretty much in an engineering sense. Okay. So, that is why today only the modern idea of is popular. So, if you say you are working on soft decision decoding of Reed-Solomon codes, you give a talk in a conference, there might be 2 people sitting and listening to you. Okay. So, it is not a very popular area and people do not work on it, but I think it is an interesting problem anyway. Okay. So, let us see what to do if you cannot do hard decision decoding, and that is soft decision decoding. So, let me write that down a little bit once again so that you see what I mean by this. Okay. So, remember I am going to stick to binary codes and we will start by example. Okay. So, we will see very simple examples of how to do soft decision decoding, you will get the idea and then we will see more generic structure for it. Okay. So, what is the overall picture again? Remember I have a code word. Okay. So, I am going to start with code words. The mapping to bits, the message bits is kind of trivial in a way. Okay, suppose you have an NK code. Okay, all codes are going to be binary from now on. Okay, so unless some huge exception, all codes will be binary from now on. So let us just say NK code. Okay, this is going to go through BPSK. Okay, BPSK will always be 0 going to +1, 1 going to -1. Okay. And then AWGN. So, the symbol vector S AWGN Z, which is always going to be normal with mean 0 variance sigma square IID, and this gives you R. Okay. I want to have a decoder here which will produce C hat. Okay. So, this is kind of similar to the problem for a binary symmetric channel. We also started like this for the binary symmetric channel and we looked at some situations. This is a very generic situation which comes under detection, etc., etc. Okay. So, people know what the best thing to do is. Okay. So, it is not very surprising that people know it, except that it may not be very implementable in most cases, but the best thing is always known. Okay. And the best thing is usually what is called maximum likelihood decoding. So, that is always the best possible decoder. So, the optimal decoder okay, is usually the maximum likelihood decoder. So, what does the maximum likelihood decoder do? Hopefully, you remember this. I derived it in fairly general form early on in the class. I do not know if you remember. No. Okay, so let me write down. C hat is you are going to maximize the probability of R given C equal to U over all U in the code. Okay. So, this is what we are going to do. I am writing probability, but clearly R is a continuous distribution. So, obviously it will be some PDF. I am simply writing probabilities just to avoid all those clumsy notations. Okay. So, whenever you have a continuous distribution, interpret PR as a PDF. Okay. So, that is the idea. Okay. So, actually I should be careful here. This is optimal only when all the code words are equally likely. So, that will be something that we will assume. Okay. So, all code words equally likely, something we will assume a priori equally likely. Okay. But computing this expression is a daunting task. Okay. So, let us try and compute it for some simple cases. Okay. So, I think the time is coming to an end. So, I am going to stop in a little while, but we will try and compute this maximum likelihood decoder for some simple cases, and then we will see it is a little bit non-trivial to do it. Okay. So, particularly for large cases, you can imagine why it is very difficult, right. How many computations do you have to do?
Per k.
Yeah, 2 power k is huge. You have 2 power k code words, and if k becomes like 5000, then you can't do this, right. So, it is very difficult to do this computation. You might think there is a way to simplify this. Okay. Yeah, there are ways to simplify it for BPSK. I will show you some simplifications, but even then the number of computations you have to do is really large. Okay. So, you can't simplify it much beyond the difficult part. Okay. So, there is also another way in which you can define optimality. Okay. So, this is optimal for what? This minimizes what? Probability of what? Which error? Minimizes probability that, yeah, that is very important. It minimizes the probability that C hat is not equal to C, okay, the entire code word. Okay. So, this is optimal according to what is called as block error rate. This is called block error rate or frame error rate. Okay. So, it is also possible to define optimality with respect to bit error rate, okay, and that turns out to be much more interesting in the modern sense, so to speak. Okay. So, that is also useful. Okay. So, we will stop here for this lecture. After a break, we will pick up from here.